Cool. So, okay, presentation. Okay, people, you can see the screen, I hope.
Yes,
Yes,
sir.
sir, we can.
Great, great. Just let me see one thing. Great. Hmm. Uh, right. This becomes better, right? You guys can see the cursor better, I guess.
Yes, absolutely.
Hmm. Yeah, okay. Somehow, this had escaped my notice that you can do it on PPTs. Anyway, so we are at the level of the community. We are looking at various interactions between species which lead to the formation of the community structure, and we are done with competition, and we defined competition as a set of interactions which are non-trophic, which means nobody is eating anybody. So what happens if people are eating each other? So that's when, broadly speaking, they come under this umbrella of predation. And wait, okay, so if I do this, then I lose the ability to transit slides. Okay, so what is predation? So predation is the process by which an organism eats all or part of another organism. If both the organisms belong to the same species, we call it cannibalism. Otherwise, we call it predation. Uh, why study it? Because it's important pretty much everywhere we look at. In terms of economics, it's important in terms of managing your pests, in terms of managing resources like fishes and other things, wildlife resources. Ecology may it plays a huge role in organizing the community. If you are trying to conserve a species, you have to explicitly take into account the prey-predator interactions. And then, as we are going to see towards the later half of this topic, it has a huge role to play in terms of evolution. So if you define simply as one animal eating another, then, or one species eating another, then there are several subgroups in which you can categorize those interactions. So suppose you have a case when one of them is a plant and the other is an animal. So the prey is a plant and the predator is an animal. Then typically you give it the name herbivory. When you have an animal being eaten either by another animal or a plant, then you typically call it carnivory. You have a special case in which the predator doesn't eat the prey directly, but it lays eggs inside it, on it, or near it, and then the offspring are the ones which end up killing the prey. So that is a special case called parasitoidism. You have another case in which the organisms derive food from the host, but they don't kill the host. They don't consume the host's body parts directly. Many cases they essentially consume the nutrients that the host is trying to consume. So that is what is known as parasitism. And as I pointed out, when the prey and the predator belong to the same species, you call it cannibalism. So mathematically speaking, obviously there are minor differences here and there in terms of how you model them, but we are not going to go into these distinctions. We are going to model it simply as one species eating another. So predation is something that the process plays a huge role historically, because one of the most famous graphs in whole of ecology is this one that I am showing you over here. So this in Canada, they have this practice of hunters hunting animals and then selling the pelts to various companies. Now, one of these huge old companies was this company called the Hudson's Bay Company, and these guys used to buy these furs from local hunters or trappers. And because this was an economic thing, an economic activity, therefore these guys kept excellent records of how many furs or how many pelts of different species are being received. So this data set, in the context of these two animals over here, the snowshoe hare and the lynx, this was something that came to the notice of a very famous guy called Charles Elton, and he was immediately struck by a very peculiar thing over here, which is essentially oscillations. So you can see that, the numbers, and remember these are in some sense proxies, these are not censuses, these are, fur number as a proxy of population size. So if you see them, then these numbers, they are undergoing periodic oscillations, but these periodic oscillations are unlike our limit cycles where the values are roughly similar. That's not really happening. You have, up down of varying magnitudes. And the other thing that you can see over here is typically the, upswing, the peak in the predator numbers is slightly delayed from the peak in the prey numbers. So the preys peak first and then the predator numbers peak slightly after that. So this particular data set and this particular graph has essentially, piqued the curiosity of ecologists for the last several years, and a huge number of papers have been written in trying to understand why this is happening. So since this is a natural thing, natural data set, then people assume that, look, there is a possibility that this is happening because of some extrinsic factor. So there are some outside environmental factors which are cycling at a particular rate, and that rate is then what is governing this oscillation. So one theory that held some sway for some time was 11-year solar storm cycle, sunspot cycle, sorry. Okay, so you know that in astronomy, every 11 years or so there are these sunspots that emerge, and people are able to show some associations between that and this. Other people said that, okay, maybe there are some climatic ups and downs which can explain all these things. And then there were other people who said that maybe none of that is true. What is really happening is that this is coming entirely because of endogenous dynamics. It's not mirroring some other external factor, it's the internal stuff itself. For example, as we saw in the case of those, logistic models and Wicker models, etc. So it's the endogenous dynamics itself which leads to these kind of regular oscillations. So to understand what exactly is going on, we will, yes, so that's what I mean. What is causing this factor? This was a major question that existed for quite some time in ecology. Now, one of the people who ended up trying to model this was again, Lotka and Volterra. So what we'll do is we'll quickly look at the rather simplistic model that Lotka and Volterra came up with. So, so since prey and predator, both of them begin with H, typically in this case you call the prey as, you call the prey as host and model it or denote it by H, and you call the predator as predator and you model it by P. Okay, so dH dt, the rate at which the host population, the prey population, is changing. So what Lotka and Volterra assumed was that in the absence of the predator, there is nothing that is going to control the prey density. So in the absence of the predator, prey will grow exponentially. Okay. So, however, we know that that's not what is going on. We know that the predators, they are bringing down this growth rate. And in what way are they bringing down this growth rate? So it's assumed that the prey and the predator are essentially moving around in the area, in the space, and when they're moving around, then they are encountering each other at a rate which is proportional to how many preys are there and how many predators are there. So essentially, the rate of encounter is proportional to number of prey and the number of predator, and you are going to require some constant for, you know, converting that fraction of encounter which is becoming a kill, right? So this is the prey equation, dH dt equal to RH minus AHP. Now, what happens to the predator equation? dP dt is equal to, now this AHP over here, this is what? This is the number that is being killed. Now, whatever number of prey is being killed, that ultimately is what is the resource gained by the predators. Therefore, that is what is going to determine the increase in the rate of the predators. So now obviously every, all the kills made will not translate into, that many number of predators. Therefore, you need a separate constant over here to scale the, in some sense, the efficiency of the predators to convert the prey biomass into corresponding number of predators, corresponding number of predator babies. Now note that here C is a constant, A is a constant. So actually you can multiply the two and get rid of one of those two constants. And many books actually do that. So they will, replace this with some B or something else, some other constant. But here, just for the sake of understanding, I'm keeping these two constants separate. Okay. And so this is the rate at which they are going to grow. And it is further assumed that they have a rate of death which is density independent. So the death rate, that is this M thing over here, this is what is density independent. Obviously, the number that is dying is density dependent, right? So this is the number that is dying. And this is what is the predator equation. So as you can see that this is a rather silly model, and this is made up of assumptions that are way simplistic, right? However, one can still play with this a little and see what is it that you are getting. So obviously, in order to analyze this, you first draw the isoclines. So for that, you set dH dt equal to 0. So when you are going to set dH dt equal to 0, then RH will become equal to, so if you set dH dt is equal to 0, then this happens when RH is equal to AHP. So you get rid of that. Okay, sorry, the A remains. Okay, so which implies that P is equal to R by A, right? Similarly, for the other one, you said dP dt equal to 0, which means that CAHP is equal to MP. So get rid of the P's, which means that H hat is equal to M by CA, right? Now, what is this leading to? R is a constant, A is a constant, M is a constant, C is a constant, A is a constant, right? So what will be the nature of the isoclines in these cases? Given that P hat and H hat, both of them are essentially giving me constants, what will be the nature of the isocline? So remember, for this, what I'll have to draw is Huh? This is prey. This is predator. Huh. So what will be the nature of the isocline?
There will be straight lines parallel to the axis, right?
Exactly. If it's a
No.
constant, huh, if it's a constant, then it has to be a straight line parallel to the axis. One will be like this, okay, and the other is going to be like this, right? So this one is the one which is corresponding to this one. So this is the dh dt equal to 0, dh dt equal to 0 line, and this is the dp dt equal to 0 line, correct? Think about this. What is this? This is the number of predators which will hold the prey population to be constant, and this is the number of prey which will hold the predator population to be constant, correct? That's exactly what is meant by dp dt equal to 0 and dh dt equal to 0. Okay. Now think about it, the same kind of stuff that we did with the Lotka-Volterra competition thing. Let's take one of these quadrants. So let's take this quadrant. So in this quadrant, what is going to happen to the prey numbers?
Sir, we can't see your pointer when you're pointing in this.
No, I am not pointing. Okay. Sorry, but you are not able to see that cursor also.
We can see your cursor, but not the pointer which you're using.
No, see, now I am on a different thing. I'm no longer on PowerPoint. So on this one, you will only see the cursor. You won't see the pointer now. So treat the cursor as the pointer.
Okay.
Okay, I'll just make it simple for you guys. What is this? This is the number of predators which is holding the number of prey to be a constant, the growth rate to be a constant, right? So if it is the number of predators, then if I have less predators, what will happen to the prey numbers? They will increase or decrease?
Increase.
They have to increase, right? So below this line, prey numbers can only increase, right? And by the same logic, above this line, prey number will decrease. Now this is the number of prey which is going to maintain the growth rate of the predator at a constant, right? This one. So if I have less prey than that, so the predators have less to eat, so what will happen to the predator number? Less food, growth rate?
That decreases.
Growth rate will go down, correct? So on
Yes.
this side of it, on the left hand side of this will only go down, and just one sec, let me erase this bit. Okay. So on the left hand side of it will only go down, and on the right hand side of it will only go up,
Yes.
correct? So this is it, right? So let's draw.
But it should go up.
It should go up,
Yeah,
sir.
I have made a mistake. Just 1 second. Correct. So when there are more prey, then it should go up, correct? And in this case, this one is like this. So this vector is going to be like this. This vector is going to be like this. This vector is going to be like this, and this vector is going to be like this, correct? So if this is what our vectors are going to look like, then what kind of a behavior do I expect?
Oscillatory.
Oscillatory, exactly. So let me now take you guys back to the PPT. Okay. Sorry. So this is what the whole thing looks like, and this is what the dynamics looks like. right? So what I'll do is now I'll quickly now I'll quickly show you guys a populous simulation. Did anybody play with populous?
A little bit.
Okay. I strongly recommend that you guys play a lot with it, because there are awesome things that you can learn over here. Anyway, so this is the Lotka-Volterra thing. There are multiple variants of Lotka-Volterra. Some of those we are going to do, and we will make it this. So this is the time series that it is showing. And can you guys see the graph over here? This stuff over here, the circle?
Yes.
Great. So now one can play with it, and one can see the effects of changing the various parameters. But essentially what you will see is that whatever you end up doing, end of the day you are just going to get these oscillations and nothing else. Okay. Okay. So this exhibits only oscillatory behaviors, and what I am not showing you over here, but you can do the stability analysis and figure out for yourself if you are so inclined, that the kind of equilibrium that you get over here is what is known as neutrally stable. Okay, what does that mean? That means that so this is the kind of oscillation that we got, right? Now suppose you end up perturbing the system. Let's say you end up reducing the number of predators such that the system is now here. When the system is now here, now it will essentially undergo another oscillation like this. It will not try to come back to this old trajectory. Okay, and then from here, suppose you reduce the prey number and you bring the system here. Now it is going to do an oscillation along this trajectory like this, right? So this kind of a system where the stability type is such that if you change the system state, then it becomes stable at whatever new state you take it to. It becomes stable around that. This is what is known as neutral stability. So the Lotka-Volterra prey predator model is a classic textbook example of neutral stability. Okay. In the course of this particular class, course, we are going to meet this neutral stability one more time when we do Hardy-Weinberg equilibrium. All right. Okay. So that is that. Bolo.
The intersection point is unstable equilibrium, right? Because they are, if you
Yes. No. Nothing is unstable over here. So what you are talking about is this point, right? This point that I just showed with. No, so this is not unstable. This is again neutrally stable, because suppose you slightly change the state of the system and you bring it here. Now it will never go back to that. It will now start oscillating like this. Okay. So that intersection point is just the point where neither the prey population is changing nor the predator population is changing. No oscillations. You perturb it slightly and oscillations will start. Okay.
Sir, so in principle, according to this model, if we collect the data of prey and predator population, only one data point, we can get the whole trajectory, right?
If you have the parameters, yes. If you have the parameters, yes. How? I mean, are you talking theoretically or are you talking in terms of data?
No, theoretically, the model needs only one data point to uniquely determine a trajectory.
Yes,
right?
absolutely. It just needs one initial N1 and number of prey and number of predator. That's it. Okay. The rest of it will follow. Okay, no, it's a completely deterministic model. Okay, Now, interestingly, we go back to populace, and now we look at the time series of. Okay, I have to reduce this a bit. Just one sec. So, okay, let me just show it to you from here right now. So if you look at this, note this black thing that you see, this one is the prey wala curve, and this is the predator wala curve. And note that the peak in the predator curve is slightly after the peak in the prey curve, right? And if you go to your populace simulations, you can satisfy yourself. This is another feature that you will recover most of the time from a Lotka-Volterra model, that the predator graph is slightly offset from the prey graph. And that, again, if you remember, I showed is one of the properties that you often end up seeing from this kind of natural data. So this Lotka-Volterra is actually also capturing that particular aspect of the data, that particular observation of the data. This I already talked about. This is a neutrally stable population. Now, note something very peculiar, that when you note when you are, let's say, perturbing the population, and let's say from an inner smaller circle you are sending it to a larger outer trajectory, then it is possible that because of this perturbation, this will now start doing this bigger circle, and therefore now it will come very, very close to this point, where if you look at it, prey population density is actually going very close to 0. Okay, now theoretically speaking, that's not a problem, because in the Lotka-Volterra it will never hit 0, it will come back, like this. However, what this is suggesting is that in a realistic population, if such populations actually follow this model, then by reducing the predator number over a slightly longer time frame, you can actually end up wiping all the prey. Okay, counterintuitively, because intuitively speaking, you think that when you reduce the predator number, then the prey numbers are going to increase. But what this model is showing is that there is a possibility that this can also wipe out all the prey. This is just a theoretical thing. Okay, we are not even talking about how it happens in real life as of this moment. So what are the major assumptions? There are quite a few, and they are rather heavy assumptions. So for example, if you remember, I said that dH dt is equal to RH when there is no predator, which essentially means that the only factor that is controlling the prey number is the predator number and nothing else. This is a problematic assumption, because we know that even in the absence of a predator, at some value or the other, the prey number is going to be intrinsically determined. There will be density dependence kicking in. It assumes that the predator is a specialist and there is only one prey. So whatever is happening to this prey that is directly affecting the predator, it has nowhere else to go, again, which is something that doesn't happen all the time. It assumes that there is no change in environment, which is basically saying that all the parameters are constant. That's true of pretty much any model. And this is also assuming that the prey and the predator, they are encountering each other in a homogeneous environment. Okay, and that is why their rates of encounters are proportional to their numbers, and scaled by a constant, and that's it. There is nothing else. The moment you bring environmental heterogeneity into the picture, then this simple assumption no longer holds true. Okay, so now the question is, how are you going to make this more realistic? So given that I have given you a list of ways in which it is unrealistic, it's pretty obvious what are the ways in which you can make it realistic, right? So can you guys come up with one or two quickly?
So one would be density dependence, right?
Straight away. First thing is, what happens when you introduce density dependence in prey? What else? Hey, come on, what else?
So we
just
could
take
also
each point
introduce
and
noise,
turn it
right?
inside out. You introduce what?
Noise in the, so there is this
Noise
K
can
parameter, because that
noise
could
can be always introduced to any parameter. That's not an issue. What else?
yeah.
Introduce
So we
more
can.
praise.
Introduce a
More praise.
right. A second prey, a third prey, and so on. Fair enough. What else?
So isn't that given, saying that the predator is a specialist?
It is in the Lotka Volterra. That is what is happening.
Okay.
Okay.
So one more thing you could do is say that the prey have like a specific breeding season or something like that, in which the number of prey increases at a very high rate in some specific period and then nothing otherwise.
Okay, some kind of a temporal heterogeneity.
Hmm.
Okay, possible. Then you have to essentially bring in some kind of a time delay kind of stuff, because the predation will keep on happening over the entire period of time, whereas the prey birth is kind of like the wildebeest, very windowed in the year. Okay.
So there will be
Bolo.
competition between the prey and predator for other resources as well, right? It's not only food, no, it's water also
Yes,
and
yes,
other
yes, yes,
resources.
yes.
So
So
we'll also have to introduce some sort of interspecific competition. As somebody pointed this out, I think in the chat box
yes.
also.
Okay, I'm not looking at the chat box, so I can't figure out. But yes, this is true that the prey and the predator can also be competing for some other resource, in which case a competition interaction also needs to be modeled in the whole case. Okay, fair enough. So you guys have some 4 or 5 ways of doing this. By the way, each one of them have been nicely studied in ecology. Okay, so any ecology textbook you pick up, slightly advanced, not 101, say 102 level, then you are going to get explicit treatments of each one of them. So one of those we are going to do right now. Bolo?
So you could also have like genetic adaptation in the prey, right? To like avoid being like with time,
Yes.
they avoid more and more being.
Yes, when that happens, then essentially your parameters will keep on changing. Yes, you are right. We will come to that, although we won't come to it mathematically, but as a phenomena, we'll come to it towards the end of this topic. Not today, tomorrow or day
Sir?
after.
Sir,
Bolo,
isn't
bolo.
that analogous to saying that the prey and predator are evolving? Like if there is
Yes,
genetic things coming on.
absolutely. It is.
Okay.
Absolutely. Okay.
But
So, bolo.
we could have colonies, and then those colonies have a random chance of meeting.
So, what will happen because of that?
I mean, the fourth assumption will be like made into better something.
Okay. No, but the fourth assumption is not about mating. The fourth assumption is about the
I was
fact.
talking about meeting, not mating.
Oh, acha, meeting. Sorry. I heard it as mating, and I was like, okay. Yeah, absolutely. So, some of these conditions we are going to see right away. Okay. So, let's take the simplest case, making the prey growth density dependent. Okay. So now instead of having where is the pointer? Yeah. So instead of having this simply as RH, I have it as RH 1 minus H by K. The rest of it remains exactly the same. Okay. If you guys have pen and paper, solve karo quickly and tell me what happens.
Sir, why not? Why are we not making predator population also density dependent?
You can do that. There is nothing stopping you from doing it. But let's start with the simple thing over here.
Okay. I thought there is some.
No, absolutely
something.
not. Obviously, I will take you to those things. इसके बाद ही करूँगा वो वाला. Okay. Okay. So while you guys are doing it, let me quickly show you guys how this is going to work. Okay. So what I said is that dH dt is equal to RH 1 minus H by K minus A into H into P. So if I set dH dt is equal to 0, then this boils down to at equilibrium, this boils down to R into 1 minus H by K is equal to AP, right? Which essentially means that P is equal to R by A 1 minus H by K, correct? The other one, the predator one, remains exactly the same. So now if I end up drawing the isoclines, so I have my prey on this axis, I have my predator on this axis, okay, then this is what, this is the equation of a line, right, with a negative slope. So my this equation goes like this isocline goes like this, and my other isocline still remains a straight line. Now that straight line, depending on what the values are, can be either here or here, wherever. Okay, so let's for a moment assume that my straight line is over here like this, correct? So I again have 1, 2, 3 and 4 zones. So if you do the vectors for these, the vectors will look pretty much what it looks in the Lotka-Volterra case, except that here the nature of the dynamics is going to be slightly different. In what way is it going to be different? That, for getting to that, I need to take you to Populus and I can show you. So this is the second case that they are looking at, which is the DD prey. DD is density dependence in prey. Okay, so this is the time series. What is more interesting is this one. Can you guys see this stuff? Can you guys see that this is where you start, and then essentially you end up coming to a stable point, which is the intersection of the two graphs, the two isoclines. Okay, so essentially what happens is you get oscillations over here, but the oscillations are of dampening nature, which means end of the day you will get to a stable point where neither the prey number is changing nor the predator number is changing. Obviously, if these two things don't intersect with each other, then you'll get a slight difference, but even in that case all you are going to get is a stable point and nothing else. Fine. So is this making sense, people, whatever I just said? Hello?
Sir, is it the same for all domains, all starting points?
Yeah, that will happen for all starting points. The only difference in behavior is going to happen based on whether those two isoclines are intersecting or not. If the isoclines intersect, they will always come to that point. Okay, I mean, you can satisfy yourself to that using Populus. Bolo?
Sir, if the isoclines meet on the x-axis, so will the predator be driven to extinction then?
Yes. Yes. So what you are saying is this point.
Yeah.
Yes, absolutely.
But that seems very weird that prey is driving predator to extinction.
Not really. We have not yet come to that. Okay. So this is what you are getting in the context of if you introduce this particular thing. So there is one more stuff that people have done. Now this stuff, it's best if you think of it graphically. Okay, there are mathematical equations behind it, but they are slightly more complicated. The graphical representation is much simpler. So remember, the isocline of this one, the prey, was actually a straight line over here, right? But if we assume that there is density dependence in the prey, then we saw that this isocline on this side is going to fold down like this, right? Instead of going straight, instead of going straight like this, this isocline is going to fold down. each time I have to do this separately. So yeah, so normally the isocline is a straight line like this, right? So the moment you have density dependence, what happens is this side of the isocline folds down. So let's assume that this is this part. Now suppose you have another realism, which is that for many species the maximum growth rate is not at this equal to 0, but the maximum growth rate is at for some value, or let's say the growth rate starts for some value which is greater than 0, which essentially means if the population size is too low, then the growth rate is negative. Okay. Now this effect is what is known as the Allee effect. A-L-L-E-E, Allee effect. Now if you put in the Allee effect, then one can mathematically show then that the effect that it has is now it will bend the isocline on this side as well. So now instead of having a straight line parallel to the x-axis, it cuts the x-axis at 2 points. Now obviously this point is the carrying capacity K for the species, for the prey species, and this point is the Allee threshold, whatever you call it, A or whatever. Now the exact shape between these 2 points doesn't really matter, but the point is that it is expected to be some kind of a hump between this and this, these 2 points. Now if you simply incorporate this stuff, then let's assume that nothing is happening to the predator wala isocline, but if you assume similar things about the predator isocline, again the behavior will not change. Then one can graphically do the isoclines and show that you can get two behaviors depending on whether the predator isocline is cutting the prey isocline on this side of the hump or that side of the hump. If it cuts the prey isocline on the right hand side of the hump, then you will get an oscillatory approach to this stable point. To this intersection becomes a stable point. It will oscillatorily approach there. However, if you end up not getting that, if it cuts on this side, then you get a reverse thing. It oscillates, but the oscillations are forever larger and larger, and very soon it will either hit this axis, which means all prey will go extinct, or it will end up hitting this axis, which means all predator will go extinct. Okay, so one way or the other, one of the other of the species is going to go extinct if you end up thinking of the prey isocline like this. Okay, a combination of both Allee as well as yeah. Fine. Now we have done this. Now have you guys looked at NetLogo? Are you guys aware of NetLogo? Hello.
Not really.
Not
No.
really. Okay, fine. ठीक है. So we'll stop over here, and in the next class I'm going to do something very peculiar. I'm going to take this Lotka-Volterra simulation, well, sorry, not simulation, the Lotka-Volterra framework, and I'm going to simulate it under the conditions which for all practical purposes will look like this, but I'll do it in a different framework. I'll do it in what is known as a agent based framework. And if you guys don't know what is agent based, don't bother about it. I'll explain that to you guys in detail tomorrow. But once I do the same set of assumptions in a different framework, you will end up getting something completely different, and from there we will get to some kind of conclusions. Okay, so as far as the class is concerned, I will stop the recording now. So the class